So another electrophysiological technique that is actually widely used clinically in therapeutic settings, like in a hospital, for example, is electroencephalography, or EEG. And basically, this is the graphing, the graph portion of the electrical activity of the brain. But it's a selective recording. The way it works is actually electrodes are attached to the surface of the scalp. So, typically you gotta, take a Q-tip, put in some kind of a substance with a bit of grit in it, almost like a little sand or something, and scratch on specific locations. This is so you can make a better kind of lower resistance kind of connection with the scalp. And what you're doing is you're actually recording activity of the brain, but it's electrical activity that is working its way through the meninges and the bone of your skull. And the skin. So these are the bone in particular is not a very good conductor. So you're going to get a pretty small signal actually. And in addition, you're going to get a pretty selective signal because it turns out for electrical activity to reach the scalp, the actual generators of that electrical activity, the neurons themselves, have to be oriented in a particular direction. So not all cells are going to contribute their electrical activity to what's recorded at the scalp with an EEG. And in addition, the deeper structures in the brain, that electrical activity is probably not going to make it to the scalp. So you're going to need, you're going to be having a more selective recording, largely from the gyri, and only some cells that are oriented in particular directions in that gyri. However, what you do is you sort of consistently apply electrodes in particular locations. In order to do it, this is usually you're working with the same patient again and again. You have to measure, from specific landmarks on the head. If you pull your glasses down and where your nose goes into your head right there, that's called the nasion. And then back here, there's a bump on the back of your skull called the inion. And you basically measure this distance, and then you also measure from ear to ear. And then from there, you place marks. And that's where you're going to place the electrodes consistently when the patient comes in again and again to see if there are changes in their EEG. Now, because this is a sort of selective recording, it's not so specific to every neuron, for example. The kind of information that an EEG gives you is not going to be so precise about exactly what you're thinking about and things. It's not a mind reading technology. However, it can give you pretty important information about state, right? So EEG is most effective, we say, at determining state. So it turns out that this is an EEG recording from somebody, it says here, excited, but somebody who is, let's say their eyes are open, right? And they're processing information. And let's say we're recording from, an electrode that's located at the, the caudal portion of the brain, or of the scalp. So we're recording some kind of visual processing that's going on. We're back here around the occipital lobe. And if you're actually looking around your world and you're processing all this visual information, right, you're going to see waveforms that are very low amplitude, okay, and a very high frequency, very fast. Now, the amplitude of that waveform, whether it's high amplitude or low amplitude, what that's telling you is the number of neurons that are firing simultaneously. Because it turns out that if you have one neuron that fires, even if it's properly oriented and it's in a gyrus, where that activity may contribute to, activity recorded at the scalp, you won't see it unless there's a lot of other neurons that are firing at the same time. So the amplitude of those waveforms that you see on an EEG reflect the number of neurons that are actually firing simultaneously. So if you have very low amplitude activity, well, that means not that many neurons actually are firing, at the same time. And the frequency of firing, well, what's interesting about that is the faster the firing rate is typically associated with more alertness and being awake and processing information. So when you have a low amplitude, rapid firing, like you see with that excited state that's shown there, that's actually called beta activity. This actually reflects many different subpopulations of neurons, right? Smaller subpopulations of neurons processing independently different aspects of the visual scene, of what you're actually seeing. Okay, now if you were to, so that low amplitude, fast, kind of recording that you get reflects actual information processing. Different sets of groups of neurons, smaller groups of neurons, are doing different things in terms of processing aspects of your visual world. If you close your eyes, right, and you just sort of rest and relax, you might get this slightly slower alpha rhythm, right, which is going to involve much higher amplitude waveforms. Well, actually, if you have a lot, like much higher amplitude, right, that means a lot more neurons are firing at the same time. And actually, that really reflects less information value. I mean, if they're all firing together, they're not telling you all these little details about what's going on in your visual world. Your eyes are now closed, right? So this gives you a little sense about how much actual information processing is going on, how engaged and alert you are in your sensory environment, for example, whether you're relaxed, right, and not processing nearly as much information. Then as you start to get drowsy, you start to see these higher amplitude, slower waveforms. This reflects the sort of, even less information processing. There's slower frequency and, higher amplitude, right? As you fall asleep, you actually get, much higher amplitude and much slower waveforms. You're not processing nearly as much information, as you are when you are awake and engaged, right? And where, different little subsets of neurons will be processing different aspects of your experience. If you're in a coma, I mean, look, it's just really high amplitude, really slow. Nothing is really being processed at all at that stage, at least from the cortex, right? However, if you slip into REM sleep, right, rapid eye movement sleep, which is typically associated with kind of a dream state or dreaming experiences, you switch to this kind of very rapid, beta activity, very low amplitude. You're again processing significant amounts of information. And in fact, it's really hard to tell the difference between a recording from an awake and engaged individual and somebody who is experiencing REM sleep, except for the fact that since you have these electrodes that are present, let's say on the forehead, you can see the rapid eye movement that's associated with that particular sleep stage, and it's very clear on the EEG. So the person is actually asleep but dreaming and processing a lot of information.